Hi, welcome to video 4.1c, differential equations. So these are equations that have derivatives in them. Okay, so pretty straightforward. It's an equation, so it's got an equal sign, and it's got a derivative in it. It's got a differential in it, a dy, a dx. So to solve a differential equation, and what they're going to do is give you dy dx equals. To solve it means to find the function y whose derivative you were given. What is y in terms of x? Okay, so to solve differential equations, DEs, you're going to use what's called the separate the variables method. Okay, so here's how we're going to handle this. So here's a given differential equation, an equation with a derivative in it, and differentials, differential y, differential of x. The first thing you're going to do is separate the variables. What I mean by separate the variables is you're going to bring all the y's to one side, all the x's to the other. So therefore, as you can see, I'm going to bring this dx, I'm going to multiply both sides by dx. So everything on the right has x, everything out on the left has y. Then you're going to take the integral of each side. On the left, you have the integral of 1 dy, which is y. On the right, when I integrate, I have 4x cubed over 3 plus 3x squared over 2 plus x, right? The derivative of x is 1, so the integral of 1 dx is x, and your constant. Now, some people will go, well, how come you don't have a plus c over here and a plus c over there? Keep in mind they'd both be arbitrary constants, so that if I brought the two of them to the same side, it would be simply another arbitrary constant. So, for example, if I put plus c1 here and plus c2 here, I could subtract c1 from both sides. I'd have c2 minus c1, which is just another constant. Now, what you get because of the c, it's called a general solution. There's not just one solution because c could be 1 or 5 or 7 or negative 3 or 2/3. What you get is what's called a family of curves. Okay, in numbers 49 through 50, it says find the equation of y given the derivative and the indicated point on the curve. So basically, they're giving you a differential equation, but you're not going to get a general solution this time. You're going to get a particular solution because they have given you a single point. Okay, so here's what we do. We separate the variables, so we bring the x to this side. We integrate both sides. We get 1y equals 2 times x squared over 2 minus x plus c. So the general solution, if I multiply through by the 2, would be y equals x squared minus 2x plus c. This is this family of gray parabolas you have. Every one of these gray parabolas is, for example, this one is x squared minus 2x plus 0. This one is x squared minus 2x plus 1, x squared minus 2x plus 2, x squared minus 2x minus 1, minus 2, minus 3, minus 4. So that's your family of curves. But only one of these parabolas is going to go through the point 3, 2. So what that is called is an initial condition. I see a point on the solution curve is an initial condition. So I have x equals 3, y equals 2. I take that initial condition, I replace the y's by 2, I replace the x's by 3, and that will allow me to solve for c. And now I know that my actual particular or specific solution is y equals x squared minus 2x, but the c I now know is negative 1, and that's my final answer right here. Okay? If you forget the c originally, first of all, I would hope that you would wonder why they gave you this point, because you'll think you don't need it. And you can bet on the fact that it's going to be rare that c will be 0 because they want you to plug in the point and get another value for c that is not 0. Okay, as I said, there are different ways to do this. This is one way to do it. This is the way we've been doing it, which is separating the variables, bring the x to the right, the dx to the right, and then take the integral of each side. There is an older way to do it, which is to leave the y here, bring the dx over, but instead of integrating both sides to go, oh, I want to get rid of this derivative differentiation, I'll do the inverse operation. It'll still work, but I can guarantee you this is your best bet. Okay, in 57 through 64, it says solve the differential equation. Now, in this particular case, they're giving you what's called a second order differential equation, because the differential equation they're giving you is a second derivative, not a first derivative. As a result, they have to give you two initial conditions, one about f prime at a number and the other one of f at a number. So what I'm going to do here, now here I am going to use that more recent method, which is if the second derivative is x squared, then the first derivative must be the integral of x squared dx. I'm getting rid of one of these primes by doing the opposite operation, okay? All right, so what happens then is f prime of x is x cubed over 3 plus c1. At that point, rather than trying to integrate again to find f, let's figure out what the constant c1 is. They told you f prime of 0 is 6, which means if I replace x by 0 and f prime of x by 6, I will be able to find the value c. So f prime of x is 6, x is 0, and I find out that c1 is 6. Hence, my f prime of x is x cubed over 3 plus 6. Once I have that, the first derivative, then I can integrate to get the original function. So I get rid of the prime or the derivative by taking the antiderivative on the other side. Don't forget the differential. And now this time I pull out the third. I have x to the fourth over 4 plus 6x plus c. Now I have to call that c2. I can't call it c1. Now I go back to the other initial condition. F of 0 is 3. Which means if I replace the x's by 0, I get to replace the f of x by 3, and you find out that c2 is 3. So my f of x is x to the fourth over 12 plus 6x plus c2, which happens to be 3. Now, the other way of doing it is to look at it as d squared y over dx squared equals x squared. The second derivative is d dx of the first derivative. Send the dx to the other side, get rid of the d by integrating, etc. And then you would the same place.